Okay, there we go. We're recording. Okay, so last time we had a lecture, which was 5 days ago at this point. But anyway, we were talking about second derivatives with the chain rule. Again, not in the textbook, but I think it's a really important topic. It came up a tremendous amount for me when I was doing my second major in physics long ago. And we talked about then, if you have a composition of functions and you want to take not a first derivative, but a second derivative, a second partial of the output variable with respect to, either one of or a combination of the input variables. Chain rules involved because this is a composition. How do you do that? How do you keep track of things? And we talked about all that last time. So now I want to address the question of why do we care? Right? When is this? How could this possibly ever come up? And there's a really nice example here. And this is literally taken out of my experience as an undergrad. There's this thing called the Laplacian operator. It is arguably an object of multivariable calculus. You can see it right here in the formula. It's a sum of a bunch of second partial derivatives. And why the Laplacian is important, that is a longer discussion. It's a topic for a different course. It's a conversation about physics, basically. But broad strokes, and I think pretty persuasively, if you're interested in how waves flow or how heat moves, how electrons behave, these are pretty big topics in physics and engineering, I'll say. Okay. This is one of the major players, or the major player in describing all of that. Okay, so I claim that you can rewrite the Laplacian that I have here, and I'm going to say in rectangular coordinates, in the sense that these are all partials with respect to rectangular coordinates. It's sort of assuming that the function that we're interested in here is written in terms of rectangular coordinates. Arguably, though, it might be, in some cases, easier to understand it what we'll call in spherical coordinates. And this is what I claim down here. This is what the Laplacian looks like in spherical coordinates. Now, this does not look like help. This looks like we're going the wrong direction. I mean, which one of these formulas looks nicer to you? Practically anyone would pick this one at this stage, I think. Okay, but I claim that this is actually going to turn out to be really, really useful momentarily. Now, before we get to that part, let me explain where it comes from. It comes from pretty much calculations like we just talked about on the previous page. On the previous page, we were considering a function in rectangular coordinates that we reinterpreted in polar coordinates, because that's what this left function is. It's just polar coordinates. Here, we're talking about taking a function that's initially in rectangular coordinates in 3 variables and rewriting it in spherical coordinates. All right? And so, analogous setup, a little different, right? Slightly different trig, of course, but morally equivalent. And I claim that you can straight up compute this thing right here, for example. Second partial of f with respect to theta. And it's just a matter of writing down the chain rule and keeping track of what's the function of what, and slowly and carefully. Make sure your diagram is always up to date, indicating what's a function of what, and you can just crank it out. It's not that big of a deal. It is tedious, but it's quite doable. Highly analogous to what we did on the previous page. And likewise with these other second derivatives. Now here I have a partial with respect to phi, and before I take the second partial, sure, I multiply by another factor here. But still, it remains that we are taking a partial derivative of something that's going to have existing partial derivatives in it. And so it's morally, again, kind of the same story. And likewise with this first term here. Okay, so if you were to crank the whole thing out, and I'm not even suggesting that you should, because it is quite tedious, right? But if you were, what you would find is that this monstrosity is just that. AKA, this rectangular Laplacian can be reinterpreted as this spherical Laplacian, they call it. Okay, now, why do we care? What does this buy me? Aside from making my life seemingly harder. Here's the great example. Very real world. Let's talk about gravitational and electric potentials. Now, maybe you're doing astrophysics and you've got a sun, right? It's got a gravitational field, and you're trying to understand how planets move in this gravitational field of a sun. That one of the big things you have to understand is called gravitational potential energy, right? Then on the other hand, let's suppose you're comfortably on the surface of the Earth, but you're doing electronics of some sort. Well, you need to understand how electric fields work, and they are closely connected to electric potential energy. Volts is the units of electric potential. Well, it turns out that the Laplacian, again, is the big player. It's the thing that describes in the physical world that we live in, for whatever reason, how those potentials must behave. And this is the rule. This is called Laplace's equation. Okay, so let's entertain the possibility that this might be a solution. Let's just say. Right? How would I decide if this is a solution? And I'll point out, of course, that this denominator is just the spherical coordinate rho. Said differently, this candidate function, I can rewrite it in spherical coordinates as this. And you already at this point might start to be persuaded, hey, I got to admit, spherical coordinates is looking better here. Right? And just real quick, if you think about it, I mean, just, broad strokes, if you're going to be studying something that is entirely dependent on its distance from something, from a fixed point, well, distance, that's what rho is, right? X, Y, and Z are not particularly natural coordinates to describe radial distances from a fixed center. Right? So spherical coordinates are arguably already starting to kind of make sense. But anyway, let's entertain how to compute the left-hand side, this thing here that we want to be 0. Here's our candidates. I can either compute this or I can compute this, keeping in mind that the Laplacian looks like this in rectangular coordinates, and it looks like this in spherical coordinates. And then keeping in mind that our candidate function here, f, looks like this in rectangular coordinates and looks like this in spherical coordinates. So here's our options. One or two, which would you rather compute? Now, again, at a glance, a lot of you would still pick this one because it's shorter. It doesn't have any trig in it, right? And I get that, right? But if you start computing this out, if you take the x partial of this thing, it gets a little ugly. And then when you take an x partial of that, it gets uglier. And then you got to do the same for y, and then you got to do the same for z. It's doable, but it's not a nice calculation. It's tedious. It takes a page. Okay. Now let's look at our other option down here. The seemingly bad one. The seemingly, oh my gosh, what a nightmare that appears to be. I claim this one is easy. We're not only going to, I'm not only going to persuade you that this is an easy calculation, I'm going to do the calculation for you right here in front of you. Here we go. Low-hanging fruit. Let's look at this term right here. Right? And let's ask, how do I apply that to this function? Well, the very first thing I need to do is take a theta partial of this function in which there are no thetas, and we are done with that term. That term is 0. We're a third of the way done. Right? I mean, that's pretty cool. That was quick. Next, let's look at, different color. Let's look at this term right here. And again, the very first thing I got to do is take the phi partial of that. And again, there's no phis in here. So 0, done. This whole, again with the colors, this whole term, gone, 0. See what I'm saying? This is pretty sweet. This is much better. Now, admittedly, there is a little bit more work to be done here, but it's still not bad. Let's watch what happens here. When I, just for convenience, I'm going to get rid of all of the markings there. When I take a row partial of this, okay, it's not 0, but aside from constant factors, there's a 1 over rho squared. And then I look at, when I multiply that by rho squared, I get just a constant. The rho squared and the 1 over rho squared cancel. And if that's a constant, then its rho partial is 0, and we're done. We have already confirmed, it's an easy calculation, we've confirmed that as desired, the Laplacian of this function is 0. And so we just accomplished something in what you might call electrostatics or, astrophysics or whatever, however you want to call it. So spherical coordinates, big win. It all comes from being able to rewrite an ugly question, right, that was in rectangular coordinates, to rewrite it in spherical coordinates. And how did we get around to rewriting that in spherical coordinates? Well, ultimately, it's about being able to do second derivatives with the chain rule. Right? So this technique that we talked about last time, this is the thing that makes it work deep down. So anyway, I think that's a cool example. Pausing real quick for questions. Anybody? Yep.
So in that first term of option 2,
this one here?
No.
Oh, you mean the
yeah.
the first on the page, not
yeah.
the yeah. Okay, gotcha.
So the partial of rho is going to be 1 over rho squared, so that is going to become 1, right?
So this is constant over rho squared, and that makes this just the constant. The constant's negative k.
Okay.
But yeah, it's still a constant is the point.
So how is that term going to come to 0?
Yeah, because keep in mind, I then have to take the rho partial of that, what I have in gray, and what I have in gray is a constant.
Okay.
And the rho partial of a constant is 0. Yeah.
Gotcha.
All right. Okay, so on to 2.6. So I want to revisit the question of partial derivatives. We talked about partial derivatives a while ago, at least a while in the sense of summer, right? Actually, it wasn't that long ago. I'm going to rewrite some of the statements that we know about partial derivatives. And bear with me, it's going to have a point. So one way to say it is that a partial derivative, it's the slope of the graph. I emphasize the graph. It's got to be the graph, right? And not everything's a graph. But anyway, if you happen to be looking at a graph, partial derivative is the slope of that graph in what I'm going to call the EI direction. I'm deliberately phrasing this in terms of the unit vector pointing in that direction, not the variable that describes that direction, because everything that I'm doing down here, my goal with all I'm writing on the screen here is to rewrite things in terms of unit vectors. I want to dissociate from variables and reinterpret everything in terms of unit vectors. So, slope of the graph if you're moving in the direction of that unit vector. It's also a multiplicative factor, right? This is another interpretation of a partial derivative. It's what you multiply by input change to get output change. Again, this is all assuming that you're moving in that direction. Again, I'm rephrasing that in terms of a unit vector. Forget about variables. This is in terms of a unit vector. Now, if you look back at our definition of a partial derivative, there was this business about holding all of the other variables constant and then taking the regular plain old single variable derivative of the resulting single variable function. It's a nice exercise to persuade yourself that that's what this is. This is written differently, to be fair, but just to get you started, notice that because EI has a bunch of zeros in it, right? This term here, t times ei, for all except for the ith variable, that's 0. Right? And so if this represents how you're moving, as t changes, well, it's got zeros in all of the positions except for the ith variable. And so effectively this is taking the derivative where we're assuming that all the other variables are constant, because here all of the other variables are literally constant. They're not changing. Anyway, there's stuff to be worked out there. I think this is a healthy exercise. Give it a try. If you get stuck, I'm happy to help. Come to office hours. I'll walk you through it. But this is a rewrite of the definition. And notice, per the theme, this is all written in terms of a unit vector. Nowhere in here is it talking about variables, x1, x2, etc. This is rewritten in terms of vectors, unit vectors. And then now here's just an observation. Recall, of course, that a gradient is a vector whose elements are partial derivatives with respect to the various variables. And so if I do its dot product with a standard basis vector, dot product with mostly a bunch of zeros, what this does is this picks out the ith entry in that gradient, which is the ith standard basis, the ith partial derivative. So that's just kind of a clever observation. But notice what this is a statement that's entirely written in terms of unit vectors, right? No variables being described here. Okay, so what's the big idea of rewriting everything in terms of vectors? The big idea is this. If you think about it, there's nothing particularly magical about standard basis vectors, right? So here's my standard basis vectors, hand gesture, in 3 different directions, and they're unit vectors, okay, sure. But aside from clinging to coordinates, and they do look uniquely cool with respect to coordinates, right? But aside from that, there's nothing magical about these vectors. In fact, if you think about it from a change of basis standpoint, right? Think flashback to Math219. You can do a change of basis. Any function could be written with respect to a different basis. So nothing at all really magical about these particular unit vectors. So one would speculate that if you have a bunch of related facts that work for certain unit vectors, why wouldn't they work for all unit vectors? In some appropriately interpreted. That's the pitch I'm going to make here. Now, I could go through and algebraically prove the results that I'm about to claim, but rather than do that, that's a bunch of tedium. It's basically applying the chain rule, set up appropriately. Rather than do a bunch of algebra, I just want to make the case that you should view statements about unit vectors that apply generally to a category of unit vectors. Why wouldn't they just apply to all unit vectors? And in fact, this is true. So what we're going to find is that there's something that we can define that's going to look a lot like this, which will be let me be careful with this. It's going to look a lot like this. And it's going to be computed by that formula, and it's going to be the slope of the graph, and it's going to be a multiplicative factor, all with respect to moving in not the EI direction, not with the vector EI, but with just other unit vectors in that place. And here it is. It's something called a directional derivative. It's just terminology. But anyway, here's what a directional derivative is. It's just all the same as above, but just replace EI with any other unit vector. And so that definition formula turns into this. There's that new unit vector V instead of EI. Here's the dot product with the gradient formula. Unit vector V instead of EI. Slope of the graph as you move in the V direction instead of EI. And multiplicative factor as you move in the V direction instead of EI. So I'm just going to assert that, now, again, I'm not going to prove these formulas. Proofs are in the book if you want to see them. It's perfectly fine. It's just a bunch of algebra. I just want to point out that this is morally the same idea as a partial derivative. And I encourage you to think of it that way, that this is just the same as a partial derivative, just why are we tied to moving in the direction of the axes, the, let's face it, arbitrary axes, right? Up to change of basis. There's really nothing magical about it. Okay, so this is called a directional derivative. Again, defined by this formula. Typically more conveniently computed with this formula and interpreted as slope of the graph or multiplicative factor, just like partial derivatives were. Okay. Alrighty. Let's say a quick word about notation. Here's the notation to represent directional derivatives. You do have to indicate what the direction is that you're moving. Right, so that's whatever that direction is that you're moving from your starting point A. Well, you got to indicate that in the notation, and it's as a subscript of this capital D. That's just a standard arbitrary notational choice. Okay, of course, you also have to indicate where you are starting from. And said differently, where you are interested in that directional derivative. Right? So there's two things. There's where are you at and in which direction are you going. Okay. And then obviously, of course, you have to indicate what function you're taking a derivative of. That's hopefully clear. Okay. So that's what this means. Do keep in mind, and this is important, the vector, well, let me do it over here. The vector indicating that direction, that does have to be a unit vector in order to do what we want it to do. So this is not just any vector you feel like. The fact that it's a unit vector is important. Okay, yeah.
Why? Why is it important?
Yeah, it's a great question. Let me sort of rewind a little bit to the question of what's so special about standard basis vectors. And I'm going to say it a little bit differently. If I have standard basis vectors like this, from your point of view, right? If I turn my head to the side, they don't look like standard basis vectors anymore, right? And so, perspective is the argument that I was making in some sense for why these standard basis vectors aren't that important. I can just turn my head to the side and whatever. But when I turn my head to the side, they do still look like unit vectors, right? So, if I were to allow using any vectors, this is no longer sort of just this is no longer a statement about directions. This is also a statement about magnitudes. And so you should at least be suspicious that if you change the magnitude in addition to the direction, slow down, it's not clear what would happen. Is that believable?
Yes.
Yeah. Cool. Okay, so now real quick, I want to give you a picture. So slope of the graph in the V direction, let's talk about that. Well, the V direction is, given a starting point A, the V direction just says, all right, well, for this other unit vector V, as I move in that direction, namely if I were to take a cross-section, let's see if I can do this competently, cross-section, still a vertical cross-section, just in the direction described by that vector, not parallel to an axis or, in the direction of increase of a single coordinate, right? Axes and coordinates aren't what we're talking about here. We're indicating the direction by this unit vector. So you just take that vertical cross-section in the direction described by the vector. That cross-section of your original graph is going to be some curve. And, of course, that curve will have a tangent line, and that tangent line will have a slope. So that's all we're talking about. Okay. And then, now let's talk about this business about multiplicative factor. Keep in mind, per partial derivatives, it's what you multiply by what I'm going to call change in that direction, input change in that direction, to get the output change as you move in that direction. And just looking at this algebra right here, now this is arguably single variable calculus, kind of, right? Old news. Single variable chain rule down here on the bottom, sort of a statement about differentials on the top there. From the point of view of these equations, what is in those equations the multiplicative factor? And well, here it is. It's df/ds. So this is another common notation. I guess I will zoom out a notch. Another common notation, or shorthand interpretation of what a directional derivative is. It's df/ds. It's the rate of change. Let's see here. Let me highlight. It is the rate of change of your function with respect to distance traveled in that direction. So df/ds. Rate of change with respect to distance traveled. So I distinguish that from rate of change with respect to time. Different story, right? But rate of change with respect to distance traveled in that direction. So nice interpretation, sort of additional interpretation of directional derivative. Okay, let's do some examples. See how the rubber meets the road here. We've got a function, and the question asks, what's the slope of the graph? And when you see that, before you even finish reading the rest of the question, I encourage you to have a strong instinct that because they asked for slope of the graph, I mean, you're kind of almost a given, looking for a directional derivative, because that's what the directional derivative is. Okay. All right, now there's some details here. We're at a given point. We're at the point 3, 1. Okay, fine. That's where I'm going to be evaluating this. Fine. We are moving with a velocity that's given by this vector. Wait a second here. Now, that's not a unit vector. Directional derivative requires that this be a unit vector. I need it to be a unit vector so that I can interpret the directional derivative as a slope. So what I really need is not this given vector, but I need the unit vector that points in that same direction as my direction vector for this directional derivative. This is an important little detail. It's easy to mess that up. So you got to distinguish between a vector and the direction that the vector points. Right? We typically, and certainly on the previous page, we describe directions by unit vectors. If your vector is described by a non-unit vector, you have to normalize it. Now we've got a unit vector. Is everybody on board? Okay. Okay. And now it's just a matter of computation. Our formula for directional derivative, gradient.unit vector. Here we go. The gradient, okay, sure, there's some calculations that, colors here. There's some calculations that go to computing that gradient. Take the various partials, evaluate at the point where you're at, namely 3, 1. So, yeah, sure, you've got to do that. Don't forget, we've already agreed what the unit vector u is. It's the normalized vector pointing in the direction of v. That's just arithmetic. And then, boom, your dot product ends up being this. So, straight up computation. The main sort of interesting part of what we've done here is to recognize that because the question asks for slope of a graph, that we just need to compute the directional derivative. Okay, next. Oh, you know what? I do need to. There's a subtlety of the phrasing here. I want to warn y'all about the related landmine. I don't want y'all stepping on this landmine. I want to talk about this phrase, in the direction of the vector, blah, blah. Okay. So, reminder, we are at the point 3, 1. There's 3, 1. Now, let's talk about this vector here, 3, 4. Now, I emphasize vector. Got to be really careful about this. We do conflate the notions of vectors and points for notational purposes because there's a canonical one-to-one, pairing. Every vector can be thought of as a point. Every point can be thought of as a vector. It's very handy in a lot of cases. But they are not the same thing, right? This specifically is a vector because it says so. Vectors do not have a location. This vector is not a place. It's not any place on this picture. Right? It is just a vector that points, let's see here, something kind of like that, I guess. That's that vector. Here's the misinterpretation that a lot of students will make, the landmine that students will step on, and that is to misinterpret 3, 4 as a point, despite what the question says. If you would interpret 3, 4 as a point, well, that point is like, I don't know, about right here, I suppose. Now, I emphasize, that's not at all described by the statement of the question. But if you misinterpret it as a point, then I guess it would be there. And then, again, misinterpretation, students will think, oh, in the direction of, that makes it sound like you're going toward that point. And so the continued misinterpretation would be, oh, I guess the question's asking me about that direction. So this would be a misinterpretation. This is flat not what the question says, right? But you can see how, student could, kind of interpreting maybe a little sloppily, make this mistake. Right? So, of course, that describes a completely different direction. It's not at all what the question is asking. Got a wildly wrong answer. It's got nothing to do with the question as posed. Very dangerous. Right? So please do make sure to be careful about this. You have to interpret the question as written. Again, the key phrase that distinguishes the wrong interpretation from the right interpretation here is that it says the vector 3, 4. That's what means that this and the direction, which you'll recall we represented by a unit vector. And keep in mind, vectors have directions and magnitudes. The direction part of that vector is this unit vector right here. That doesn't show up very well against the purple background. Sorry about that. But this in orange there, this little unit vector. That's the direction. So, heads up. Be careful about that. Okie dokie. Another example. Again, you look at the actual question after all the setup, blah, blah, blah. The question says, right there in the statement of the question, rate of change with respect to distance. And again, that is a knee-jerk reaction, sort of like, oh, rate of change with respect to distance, boom, directional derivative. That's one of our primary original interpretations of directional derivative. So I know the question is asking me to compute a directional derivative. And directional derivatives are computed by, again, this handy-dandy formula here. And again, now the question turns into, well, pretty much plug and chug. And so I'm going to have to take the gradient of this function, evaluate at the point in question, and that is there. That's the gradient. Again, I have to find the unit vector that points in the relevant direction. Again, in the direction of. Again, be careful of the phrasing. Again, don't misinterpret as a point. Again, danger. But the direction indicated by this vector is just the unit vector pointing in that direction. easy to normalize. And again, arithmetic, and again, we're done. Is everybody good? Yep.
What's S in this question?
Yeah, so S is a typical choice for representing distance, just distance as a general concept. So when the question says, as it does here, dtds, they're saying rate of change with respect to distance. As you move in a certain direction, per unit distance traveled, as you go that way, how fast is the function changing? Yeah, yes.
How do you get that value for the gradient of t?
This right here?
Yeah.
Well, let's see here. So I plugged in this point into this formula. So x is 1, y is 0, z is 2. Looks like I factored out these 2's.
Okay.
I factored those into the that turned that into a 50, and
that was
yeah.
where I got lost. Okay.
Yeah, no worries. Yeah, all right. Okay, now with my apologies, I have to talk about a terminological disagreement, I guess I'll call it, in the community about this very definition that we just described, this term directional derivative. I am sorry to say it means different things to different people. It's very frustrating. The punchline of what I'm about to tell you is that it sadly falls to you as new members of the mathematical community to be aware of the fact that other people use the term in a different way. And it's dangerously different in the sense that it's very, very, very similar and just a little bit different. And just conversationally, it'll even sound like the same usage, but it's not. So here's what it is. In some contexts, this whole business about it having to be a unit vector, some people take that requirement away. Some people, in other words, will look at this definition here and say, okay, let's just replace EI with any other vector. Doesn't have to be a unit vector. And now, listen, they're not wrong. They will readily confess that you don't get all of the same properties. You get only some of the same properties. But they will still use the same term, directional derivative. They will use the same notation, directional derivative, that we've used for the way we've defined it in this course. And same definition formula. And good news, it's still computed by the same dot product. And this is, in fact, a reasonable definition for directional derivative. There's nothing intrinsically wrong with this as a definition. Now, you do lose, and I went on at length, of course, about how important it is. It's got to be a unit vector if you want it to be totally analogous to partial derivative and get these properties. And so when we remove the unit requirement, well, all this goes away. Right? But this remains still a pretty useful concept. I can use any vector, and a very simple formula allows me to compute how the function is changing as I move in that direction. That's very broadly useful. A lot of people prefer this definition. I'm one of them. Totally honest, right? The reason that I am not doing my personal preference here is because the textbook doesn't, right? The textbook does it the way, the textbook does it how I have it written here in the notes. Right, so I do feel that it's necessary, given that we have a chosen textbook for the course. I feel like we got to get on board with what our textbook does. But it's not my personal preference, and it's not how I define directional derivative in my textbook. And it's not how I use the term outside of Math219. Right? So anyway, heads up. Right? Just be aware we're out there. Right? And so, anyway, the solution to this problem is actually not that big a deal. It's just that you have to, when outside of Math 219, if you hear the term directional derivative, look for context clues, right? Some indication one way or another as to which they might mean. And if you can't determine it from context clues, then just straight up ask them. Say, just a clarification, which sense of directional derivative are you using? Right. Okay. All right. Okay, so I emphasize for Math 219, this is the definition that we're going to be using. These properties all apply, and henceforth in Math 219, I will not make any other references in this class to the other point of view. Okay. All right, I just wanted you to know what's out there. Okay, so here is a interesting question that we can ask now that we have this idea of a directional derivative, and reasonable question. So suppose we have some function, a multivariable function, like so. And we're, sitting at some point A. And as we sit there at that point, we contemplate our options. I could perhaps move in that direction, or I could move in this direction. There's a bunch of different directions that I could move. And of all of my options, and keep in mind, in this class, we're using unit vectors to describe directions. Right? Of all the different directions that I could move, which one is going to make the directional derivative, namely the rate of change of the output, which one is going to make that directional derivative as big as possible? It's a reasonable thing to want to know, right? I mean, that's where you're standing and it's cold and you want to get warmer, right? And if you have a function that tells you what the temperature is as a function of location, your natural question to ask is, which direction do I walk to make temperature increase as fast as possible because I'm cold and I don't like it? Does that make sense? A very, very natural question. Okay, now, so let's talk about these directions, and let's say, by the way, that let's say that this ends up being the right answer, hypothetically. Let's suppose that's the direction. How would I describe this direction? Well, this is the direction, presumably, that maximizes the directional derivative. Okay, well, wait a second here. What is the directional derivative? The directional derivative is how fast the function's increasing. So if you have found a direction that makes the function increase as fast as possible, pretty reasonable to call that direction the direction of fastest increase. I think it's very reasonable. It's the direction of fastest increase because that's the direction you go to make the function increase as fast as possible. It's grammatically very plausible. Okay, well, now, here's another thing, though. Another interpretation you can take of directional derivative is, and I missed, let's try that again. It's the slope of the graph. So if you have a direction that makes the slope of the graph as great as possible, wouldn't it be reasonable to call that direction the direction it's the direction where the slope is as high as possible. That's the direction where the graph is as steep as possible. Direction of steepest ascent, they call it. Again, just, interpreting reasonably from the fact that the thing you're trying to maximize is what you might call steepness. So both of these terms are out there. They're both reasonable. I will point out that this one down here, in this context, right, direction of steepest ascent, only makes sense if you're looking at a graph, because slope is the interpretation, only if you're looking at a graph. So this interpretation is highly limited, and so therefore this terminology really only makes sense in a highly limited context. So this is not my preference, personally, right? That said, it's the more common notation, terminology. Most of the time you're going to hear this property phrased as direction of steepest ascent. And it's slightly annoying to me. I would prefer to call it the direction of fastest increase. In this class, I'm going to go ahead and choose to call it direction of fastest increase, because this makes sense in any context. It doesn't matter what kind of picture you're looking at. This always makes sense. So I'll always say direction of fastest increase, practically always. But y'all need to be aware that you could hear either of these. Okay. All right. Does everybody understand the question and the terminology all hopefully makes sense? Okay, so how do we answer this question? Right, so here's what I want to maximize. I want to make that as big as possible. This is the formula for it. That's what I want to make as big as possible. That dot product. Oh, hey, here's how you compute dot products. I want to make this as big as possible. Right? As I consider all of my various different directions. But notice, as I entertain all these different directions, notice that my point is not yet actually moving. I'm still at the point A, which means that my gradient is actually constant. The gradient is a function of location. It's a vector that's defined and has a single value at that single location. And furthermore, all of these vectors are unit vectors, and so the magnitude of V, even though V is not yet decided, the magnitude of V is fixed at 1. So what I've got then is that now that I sort of rewrite everything, now this is the expression that I want to maximize. And how do I make this expression as big as possible? Well, I just want to make cosine theta as big as possible. And that's easy. You do that when theta is equal to 0. Theta being, of course, the angle between the two vectors that you're dotting, and so being that angle right there. And now, geometric appeal, if that angle is 0, what that means is that your unit vector, your direction of fastest increase, is the one, it's the one that points in the same direction as the gradient vector. So said differently, it's the normalized gradient. That's the unit vector whose angle with the gradient is 0. So nice fact. Another way to say that, the gradient vector always points in the direction of fastest increase. Nice fact, yes.
What about if our output is a vector?
Yeah, this is real valued only. That's a great question, but yeah, this is, I hope I wrote that down somewhere. Yeah, great question, but real valued only. Yep. Yeah, if it's not real valued, then you can't really compare output values because they're not scalars. And yeah, right. Okay. All right. Related question. So, okay, I've decided that I'm going to move in this direction. What is the value of this directional derivative? How fast is the function changing as I move in that direction? How steep is the hill if I were to start climbing in that direction? Well, how steep is the hill? Directional derivative computed by a dot product. We just agreed that V is the normalized gradient. Gradient dot gradient is magnitude squared. And magnitude squared divided by magnitude is magnitude. So another nice little calculation, easy calculation in the big scheme of things. And magnitude of the gradient's the answer. So what I like to do is to put these two calculations together as a sort of what I like to call a geometric characterization of the gradient. Now I'll remind you, up to this point, the gradient has been, originally the gradient was a notational convenience. It was just notation. Then we found that the gradient was a tool that would allow us to relate input changes and output changes. It was a kind of a derivative, but still an algebraic thing. Now we have a geometric point of view on the gradient. The gradient is the unique vector whose direction is the answer to one very reasonable question. What's the direction of fastest increase? And whose magnitude is the answer to another very reasonable question. How steep is it in that direction? And what's the rate of change with respect to distance in that direction? Two very reasonable questions, the answers to which give you the geometric features of the gradient, namely the direction and the magnitude of the gradient. So, lovely little rephrase. Okay, a little example. Suppose you are on the side of a hill. The hill is in the shape of a graph. Keep in mind what a graph is. Z is the value of the function and all that. Very important, of course. So here you're on the graph at a particular point. You are in particular at a point on that graph that's sitting above 1, 3. So 1, 3 is the point in the domain, you might say. And of course you are in three-dimensional space, sitting above that. Now real quick, I want to point out it's easy to conflate these two, and in fact it's pretty convenient to conflate these two. But when we do conflate these 2 points, don't forget that they are, of course, different. So the point in the domain describing where you are and the point on the graph, they're not actually the same points, right? But if you think about it, let's suppose you had a map, right? This is a hill that you're on and you're looking at a map and you've got a radio and you're describing to someone who's going to come meet you at where you're at on the hill. You wouldn't say, well, I'm at latitude blah, 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 and longitude such and such, and altitude what? No, you're not going to tell them the altitude. They know your altitude. You're on the ground, right? You're not flying through the air. You're not tunneling under the hill, presumably, right? So of course you're where the ground is. Of course you're on the graph, as it were, the graph, the altitude function. Nobody describes where they are on the surface of the earth with anything other than this longitude and latitude. You know? So technically that's kind of conflating two different things. Where you are on the map is a point in the domain. Where you actually physically are is a point on the graph, which is not in the domain. So heads up, right? I mean, again, interpret appropriately. You got to always think about this fact and interpret accordingly. And because in practice, we don't typically distinguish these. So in practice, most of the time, this phrasing that I used here will not be employed. Most of the time it'll say at the point 1, 3, and this whole business about sitting above that, well, that's obvious. That makes sense? Okay. All right. Okay, so the question says, which way is uphill? Which I'm going to reinterpret as which direction is the direction of steepest ascent? Which, as we know, is the gradient. So, to answer this question, which way is uphill, all you have to do is compute the gradient, specifically compute the gradient at the point where you are, 1, 3, and at that point, 1, 3, that's what your That's what your gradient vector is. And it's, let's see here, negative 2 comma negative 2 is about like that. So that's uphill, which, as you can see in the picture, it looks about right. Everybody happy? Okay. And how steep is the hill in that direction, right? So how tough of a climb is it as you go uphill? Well, how steep means getting rid of the rest of this stuff. How steep is the magnitude of the gradient. So again, all you got to do is take your gradient vector, take the magnitude, and there's your answer. That's how steep it is. Okay. Beautiful thing about these questions. Oh, yeah, go ahead.
So if the question asks like which way is downhill, would
Yep.
you just take the opposite?
Yep, it's the exact opposite. Yep, which again, physically satisfying, right? When you're climbing uphill, if you fall and start to roll, you roll downhill. Exactly the opposite of what, yeah, totally. Okay, moving along. So this next fact is another really nice interpretation of gradients and makes use of directional derivatives. This is not about graphs. Very importantly here, we're looking at a level set. No, whoops, I don't want to use red. Level set. You can see right there, we're not setting f equal to a new variable. We're setting f equal to a constant. So don't think about graphs here. Slopes are not involved in this discussion because we are not looking at graphs. This is not a graph. Okay, so, all right, we're on a level set. And I have an innocent observation to make. If you're on the level set, such as, let's suppose I'm walking around on the level set, or however you want to think about it, but suppose I'm moving along the level set on this curve right here, entirely contained in the level set. Well, I am moving entirely in the level set where f is equal to c, and so that means that along this curve, everywhere along this curve, the value of f is c. It is constant. It is literally constant. Now, another way to say that is, as I am at this point and moving along the curve, the function's not changing. Now let me say that a little bit differently. As I am at this point and moving with this velocity, that being the tangent vector to the curve, the function is not changing. Of course, it's not changing. The value of the function is constant. I'm on the level set. So, as I am at that point and moving in the direction of a tangent vector to the surface, any tangent vector to the surface, my directional derivative is going to be 0. Right? Because I'm moving along the level set where the function doesn't change, directional derivative is 0. Is everybody with me so far? And this applies to any tangent vector to the surface. There's too many to draw, of course. Well, now wait a second. This is a directional derivative, but don't forget directional derivatives. Directional derivatives are computed with these dot products. So if all of these directional derivatives are 0, that means that this dot product is 0. And if a dot product is 0, again, knee-jerk reaction, right? If a dot product is 0, that means those two vectors are perpendicular. And so we have a pretty powerful conclusion here. The gradient vector is always perpendicular. Orthogonal. Right? Dot product is 0 means orthogonal. It's always orthogonal to every tangent vector to the surface, aka gradients are always perpendicular to the level sets themselves. Gradients are always perpendicular to level sets. Really cool fact. Very handy. And this is useful regularly. Lots of circumstances, yeah.
Yeah, just a notational question. I noticed you do, when you show the derivative of a directional derivative, you do df, ds. But you mentioned f with respect to s. Why is it not partial?
Because that's a great question. As you are moving, like if I wanted to make sense out of what I mean by df, ds, I would this doesn't make any sense unless it's understood which direction you're going, right? So this only makes sense if I know that I'm moving in that direction. Well, once I know exactly what direction I'm moving, I can describe my motion by parametrizing a curve, and my position on that curve is described by a single parameter, typically t, right? But in this case, I'd parameterize in such a way that my parameter is s. So it's literally a single variable derivative. Yeah, because So there is a multivariable function involved, but this is asking a question about a derivative of a composition, where f is a function of location, but location is a function of s. So literally single variable. Yeah. Okay. All right, now the example that I have for y'all on this is, so again, tough choices that I have to make as the instructor. I just don't have time to cover everything. And I think this is a pretty straight read. So I'm going to have y'all read this example, and we've got to move on now and talk about the implicit function theorem, which is coming up momentarily. I do want to point out the broad stroke strategy, though, of what is done in this calculation. This is just a revisiting of the question of how do you find the equation for a tangent plane. And recall that a tangent plane, previously, we viewed this as the graph of the linear approximation. Right? What I want to do here, though, is point out that if your surface is originally viewed as a graph, again with the colors. If your surface is viewed as a graph, right, that graph, just by doing a little bit of algebraic trickery, and not even that bad, just kind of moving a couple of terms around, you can reinterpret a graph of one function as being a level set of a different function, right? And so this is a great example of how sometimes if you find yourself looking at a graph, but if you wish you could use the calculus of level sets, there's some cool calculus of level sets. Oh man, I really wish I could use the calculus of level sets. Just do this move, right? Just take your algebra describing your graph, move the terms around a little bit, and now lo and behold, you are literally looking at a level set of a different function. To be fair, sure, this is a new function called g. It's not the same as f. But you can apply the calculus of level sets to this function in purple. And it will apply to the surface that you're interested in, even though the surface that you're interested in originally came to you in a different form. It came to you as being a graph of some other function, but you discard all that and just reinterpret it as being a level set of this function. So the rest of it is readable details, and I'm going to encourage y'all to read through this. You'll notice that the punchline is that we literally get the same old result, namely the graph of the linear approximation that we talked about several sections back. Good exercise to think through those details. Okay, and likewise this example here. Okay, so I'm going to move on now and talk about implicit differentiation and the implicit function theorem. Here's the good news. I think many of y'all have seen implicit differentiation before in single variable calculus classes. If you haven't, don't worry about it. But if you have, cool. Here's the bad news. I'll bet you, could be wrong. Apologies if some of you had better single variable calculus classes than I'm expecting. But very often, if not usually, they sweep under the rug a pretty significant point when they do implicit differentiation in single variable calculus classes. So let me try to explain what the issue is here. Suppose we have a level set here, curve in space, curve in the XY plane. And I'm going to ask the question now, looking at this curve, can I view y as being a function of x nearby? And so if you look at this point here, there's really no problem there at that point. We passed the vertical line test, no problem. At least, nearby that point. And so, cool. So locally, for this point, yes, you can view y as a function of x. All right. What about at this point over here on that same curve? At that point, can I view y as being a function of x? And now notice the little clarification here. Locally. Can I locally view y as a function of x? And I want to be a little bit more specific. What I mean by locally is, at the point where you're asking the question, we restrict our attention to a little ball around that point. Locally means you can make that ball as small as it needs to be, right? So you don't have to pick a ball of a fixed size that's awkwardly, problematically large. No. Make it as small as you want. And in this case, I'm going to make it, let's say about like that. So looking only at this part of the curve. So locally on this curve. Looking just at what I've got in blue there, inside of my yellow region. Do we pass the vertical line test? Yeah, no problem. Looking only in the yellow ball. No problem. Everybody see that's okay? All right, now here's the actual problem. A lot of people are weirded out by this case because they're thinking, hey, yeah, but, we're failing the vertical line test. It intersects 3 times. Well, if I were asking if y is globally a function of x, then yes. But we're not. We're asking locally. Locally allows me to restrict our focus as much as I want. And that restriction of focus resolves the issue there. But if I think about this point, if I look in a neighborhood, a little yellow ball, again, thinking locally, and look at just this piece of curve here, y a function of x there, no, I crash and burn the vertical line test. So for this point, y, not only is y not a function of x, it's not even locally a function of x. Everybody see the problem? And I pose, it doesn't even matter how small you make your neighborhood, however small it is. I mean, to say it bluntly, at that point, the curve is in the process of wrapping under itself. And it doesn't matter how small you make the ball, it will have wrapped under itself at least a little bit, and you will fail the vertical line test. Okay. All right. Now, who cares? The reason we care is because if you want to talk about dy dx, and what does dy dx mean? Right? What does dy dx mean? Well, at a point like this, I really don't care about the fact that there's other points up here. That's got nothing to do with, if I wanted to find dy dx, I just need just enough curve that I can talk about a tangent line, and then I can define dy dx, the usual way, slope of the tangent line, blah, blah. But I do need, at least locally, to have y actually be a function of x, because derivative is something we do to functions. Very importantly, derivative is not defined as the slope of the tangent line. That's an interpretation that works in some cases, usually, right? But derivative is an algebraic thing, and it's something we define on functions. We do not talk about the derivative of a curve. We talk about the derivative of a function. And when we get to the point where we're thinking about this location right there, at that point, the fact that there is a little piece of curve there does not help me define a derivative. Again, we do not take derivatives of curves. We take derivatives of functions, and this is not a function. Y is simply not a function of x. It just isn't. And you can no more take the derivative of y at this point than you can take the derivative of a bicycle. It's not a function. You can't take the derivative of it. So, here's the problem then. I mean, when we have some equation like this, we like to do implicit differentiation and start tossing around derivatives of this and that and kind of applying the chain rule here and there, and we'll be writing down dy dx like that's a thing, like that's meaningful. But if this is the point that we're looking at, then y is not a function of x. It's not that we can't compute dy dx, it's that dy dx is meaningless, garbage, nonsense. It's not a thing. And we cannot have that in our work, right, in our reasoning. So before you can even talk about dy dx, much less compute it, before you can even talk about it, you have to establish that y actually is, locally at least, a function of x. So we need a way to tell the bad news case here from the good news cases here. And this tool that distinguishes the bad news cases from the good news cases is called the implicit function theorem. And it's usually left out of single variable calculus classes. So anyway, that's what we're going to talk about here. I am going to hit just kind of broad stroke highlights. We're not going to get real rigorous about this. That's not what this course is. But here's what problems look like. Problems look like this. We already said the words that it's where the curve is wrapping under itself. That's what a problem looks like. This is the bad news we're worried about. And neat observation, if the curve is wrapping under itself, that means we're going to have a vertical tangent line. Notice I did not say derivative. I'm just talking about a tangent line here, right? But we'll have a vertical tangent line, which means we will have a horizontal gradient. And now you just remind yourself, what is a gradient vector? Well, a gradient is, that's partial with respect to x, partial with respect to y. If that's horizontal, horizontal means that this second component is 0. So, said differently, if you've got a problem, that problem will evidence itself, by the partial with respect to y being 0. Everybody follow that reasoning? And this is as it stands, not a particularly useful tool. This presumes that we know the answer to the question of whether or not it's a problem or not. I need this thing to kind of go the other direction. I need something I can check implies answer to the question of whether it's a problem or not. So this is uselessly backwards. So I'm going to apply this thing called the contrapositive. I hope you all remember the contrapositive. If P implies Q, the contrapositive is not Q implies not P. Does that sound familiar? If you haven't heard that before, it's a standard logical construction. Come to office hours, I'll happily elaborate on it. But here's the contrapositive. If the y partial is not 0, that means that this doesn't happen. But if that doesn't happen, then certainly there's no way that can happen, and that means no problem. So this is morally how the implicit function theorem works, and there's details, formalities to be dealt with that we don't need to worry about. So here's the three-dimensional. Oh no, it isn't. We're out of time. Okay, we will pick up here on whatever day this. We'll pick up here tomorrow, Thursday, and so we'll draw the line right here for today. See y'all later. See you tomorrow. Okay. Yeah.
If problem implies partial of f with respect to y, then if you have a partial of f with respect to y, that doesn't imply a problem necessarily. What's the
correct? Yeah, the arrow. It's a one-way arrow thing. That's right. There are. So, for example, I mean, we could have our curve could look like something like this, where it gets momentarily vertical, but then it goes the other way. And there's no problem here, right? This is actually fine. So there's no problem, but the partial with respect to y is still 0. Yeah, exactly. So this arrow only goes the one way. Right, great question.